Another way of getting enthalpy is to use average bond energies. Now this will provide us with an estimate of delta H. And the reason for that is because we're using average bond energies here to make the calculation. And these energies are in kilojoules per mole, and they represent the average energy it takes to break a bond of each type. So if we take, for example, a CC double bond, there are many different ways that we can express a CC double bond, many different things that we can attach to it. And each of these will change the bond energy very slightly. The energy required to break each of these bonds will vary just a little bit. So the value we come up with here is an average bond energy for pretty much every known CC double bond energy that's ever been calculated. So anything we use may or may not match the 611 here. It might be a little bit different, it might be higher, it might be lower for our particular compound. That's why any value we come up with for delta H will end up being an estimate, because these are all averages. Right, so let's go back to the table here. It's just a trend I want to point out to you. If you take a look at a CC single bond, you can see that it's 347. You can see the CC double bond is about double that, and that's what we would expect. And a CC triple bond is about triple that. So you can see that the bond energies kind of go in order of the bond order from single to double to triple. Alright, a couple of other things. What we can do in order to calculate the delta H is to use this equation here. The sum of the bond energy of the reactants minus the sum of the bond energy of the products. You'll notice that this is the opposite of the way that we calculate delta H from heats of formation. When we were using heats of formation, it was heat of formation of the product minus the heat of formation of the reactant. Now the reason for that is because heat of formation was all about the heat required to form a compound. Bond energies are all about the energy required to break a bond. So that's why this goes in the reverse. So we do the sum of the bond energy of the reactants minus the sum of the bond energy of the products. Right, the other thing I want you to consider is that when we're talking about these kinds of compounds over here, for example, on the reactant side we're looking at breaking bonds, and then on the product side we're looking at forming bonds. So breaking bonds is going to take energy, and forming bonds is going to release energy. So that's how this equation is going to work. We can figure out the sum of all the bond energies on the reactant side, and then we subtract all the bond energies on the product side, because we are going to be forming bonds and releasing energy, while over here we're taking energy in. So in this instance, what we're doing is we're looking at all these different bond energies, which of course we get off the table. These are all positive values on the table, by the way. I've only made them negative just to show that this energy is being released, because these bonds will be formed on the product side. So the delta H here could be estimated at 1818 kilojoules per mole minus 1719 kilojoules per mole, which comes out to 99 kilojoules per mole. As I said, this is an estimate because there's many different kinds of N single bonds, for example. So this negative 163 kilojoule per mole value that I've got here will vary depending on the N single bond that we have, but this is just an average value here. The actual value that's calculated, 95.4 kilojoules per mole, is what we would get if we used heats of formation. And heats of formation would give what's considered to be an accurate value, while this gives what's considered to be an estimate. Alright, so let's look at an example of this. And an example would be, say, this reaction here. And what we're going to be doing is just applying this particular formula, sum of the bond energy of the reactants minus sum of bond energy of the products. And all we have to do now is just count up the number of bonds that we see. And as you can see, I've already calculated this out. We've got 2 by CC single bonds, they're here, this one and this one. We've got 6 CH bonds, there's 3 here and 3 here. We've got a C double bond O, that's it there. And we've got 4 double bonded oxygens because we've got 4 oxygen molecules here. On the product side, we've got 3 CO2s, which represents 6 C double bond O's. There's 2 in each CO2 molecule. And then we've got 6 OH bonds because we've got 3 waters and there's 2 OH bonds in each water molecule. Now, a trick that you can use here is that you can look on the reactants and product side and see if you can see anything the same. We've got 1 C double bond O over here, so I'm going to get rid of that. And I'll take off one of the C double bond O's on the product side. So anytime you've got the same bonds, you can just cross them out, treat it like an algebraic type situation. If you've got 1 C double bond O over here, we can subtract 1 C double bond O from both sides, and it just simplifies our calculation a little bit. And if we do that, we're going to come up with, for the reactants without the C double bond O here, is going to come out to be 5,170. And we are going to subtract from the product side 6,464 is what this comes out to. The 6,464 comes from the 5 times CO plus the 6 times the OH. And this is going to come out to be negative 1294. And the unit here is going to be kilojoules per mole.